just wanted to start with kind of where we left off last time. So I posted this in sort of a playlist on the Canvas site. I'm gonna think I can get some volume here.
Soil rests on a porous stone. Water is constantly supplied from a reservoir through a foot-level valve. That way, the equivalent to 6 inches of treatment for base course material was placed on the specimen. 2 scales were used to measure the amount of heat. One was fixed to the cylinder, and the other was attached to the weight and moved upward with it. To provide the freezing temperature required, the specimen was placed in a freezing cabinet. A thermoplane window in the front of the cabinet permitted observation of the specimen. Here is a diagram of the experimental setup. The specimen was placed in the freezing cabinet and surrounded with granulated cork insulation, so that only its top was exposed to the freezing temperature. The bottom of the cabinet was heavy mesh, so that the bottom of the specimen would be exposed to the constant 38-degree temperature of the laboratory cold room. The natural condition of soil freezing from the top down was thus simulated. The decrease in temperature was controlled so that the specimen would freeze at a slow rate, approximately 1/4 inch a day. As a tool to aid in the study of this slow process, a time-lapse motion picture camera was used as a recording device. A timer controlled the camera to expose one frame every 4 minutes. At the same time, it switched on the electronic flash unit, which illuminated the specimen. When projected at normal speed, the activity of several weeks can be observed in a few minutes. This is the actual appearance of the apparatus, the camera and timer positioned in front of the cabinet. Looking into the cabinet, one can see the cylinder surrounded except at the front by the granulated cork. The white wires lead to the thermocouples embedded in the walls of the cylinder, used as another check on the progress of freezing. Here is the cylinder, its base flattened to aid observation, and the cabinet window. The electronic flash is between them at the bottom. An insulating cover matching the 2 side retainers was placed over the open space between cylinder and window, insulating the cylinder base from the freezing temperatures. Now in operation, one frame of film is exposed as the electronic flash fires. Here is the film the recording camera exposed. Ice lenses are forming in the specimen. The freezing front is on the line where ice lenses can first be observed as they form. The scale attached to the weight on top of the specimen is already moving upward, indicating that heating is taking place. This specimen is New Hampshire silt, a soil susceptible to frost action. Its initial water content was 19%, almost as much water as the unfrozen soil could hold. The watch records the time of each film exposure for a later detailed study of any particular frame. As shown in this film, 1 second represents about 1.5 hours of actual time. Several days later, our camera was repositioned as the freezing front nears the bottom of the specimen. Heating observed is entirely due to the thickness of ice frozen in the soil. The water content of the specimen, which was 19% before freezing, became 55% when the freezing was complete. The 6-inch specimen increased to 10 inches in height, a total heating of 4 inches. This is nearly 70% of the initial specimen height.
All right, so just wanted to show you that to emphasize drive home the fact that, as he said at the end there, initially 19% water by volume, at the end something like 55%. So all that water being supplied by that head tank that's coming in from below. And all this space that you see in there is now ice. Sometimes you can find experiments where they somehow manage to kind of hold that freezing front in place, and then you just get a thickening lens. It just gets thicker and thicker over time. Okay. So, I wanted, and also I couldn't resist treating you to Mr. 1950s narrator, because he's sort of awesome. All right, so let's kind of review where we are and where we're going. Again, we're talking about weathering, and we've looked at some. Well, we started with posing the question, what's the mechanism for onion skin weathering? And that's sort of I hope we can kind of delay gratification and build evidence and consider the different processes until we finally can eliminate some and figure, okay, this must be it. I'm asking it because it's a common process that is not well explained in either our text or any other text or even in journal articles. And it's just sort of a real, it's like I said, it's a very common process that we kind of should be able to explain. And I think we are now at that point, just in the last few years, where we can get a handle on it. We did look at some processes last time that break rocks and looked in some detail at spallation and frost cracking, which will today finish up frost cracking and also look at root damage today. Next week we'll look at salt cracking and the chemistry of weathering in order to deal with, well, we'll kind of transition to processes that require chemical reactions but do have physical, do actually break rock, like salt cracking. And we'll also talk about just the chemical reactions, chemical denudation, and that sort of thing, and even the role of roots and trees and so on in that as well. Okay. We finished up last time, kinda. I showed you some experiments with that had to do with detecting where frost cracking occurs in terms of the temperatures. That we showed that, yeah, it's in this window below -3 degrees C and extending down to some kind of indefinite depth. And so I just wanted to review the kind of recipe or ingredients at least for frost cracking. We need cold ground. And specifically in that something like -10 to -3 degrees C, which we call the frost cracking window. We need enough water, as we saw in the experiment. They had to supply it with water. The water that would have already been in that soil column would have been depleted relatively early in the experiment had they not supplied it externally. We need time. And the more time, the more frost cracking. And we need those pores, and we need them to be the right sizes. What are the right sizes? Well, let's not concern ourselves so much with what exactly the right size is, so much as we also need the right variation in pore sizes. Because we need freezing to start in some pores, in the largest ones, while the water in the smaller pores is unfrozen. And why do we need that? Because we need liquid water surrounding these places where the rock is, where these ice lenses are forming in the rock. We need liquid water to feed that in order to get frost cracking. And keep in mind that, that within this rock, it's not necessarily going to look just like it does in one of these soil column type experiments. We're probably, at least not at first, we're not going to form these sort of layers of ice lenses. We're going to be forming ice within existing pores in the rock and that frost heave pressure is going to enlarge those those pores and crack the rock to do so. Yeah?
Along with pores, we're seeing permeability is kind of a big deal.
Yeah, that's a good point. We need, I could have probably said the right sizes, the right variation, and the right connectivity, because simply having the pores isn't enough. They have to be connected so that we have permeability. That's exactly right. And remember, we know what sets the upper limit of the frost cracking window has to do with simply that temperature, the freezing temperature for a curved water surface is below 0 degrees C. As we get colder and colder, the tension with which the pre-melted layer sucks on surrounding liquid water increases, but the viscosity of the water also increases so that the hydraulic activity decreases. So we eventually reach sort of a stalemate between that sucking power of that thinning pre-melted layer and the ability of water to actually permeate and flow through those pore spaces. Okay. I want to talk now about that time issue. That is, where are we getting again, we looked at frost cracking on that pore scale, and I want to now turn a bit to, and we've looked at this nice column experiment done however many years ago, it looks like in the 50s, based on the dialect of the narrator, I guess you'd say. Here we are in a colorblind friendly colored map. We're looking at a model, a simulated ground temperature as a function of depth below the surface and time over a 1-year period, not starting January 1st, who knows, starting say sometime in spring when we're kind of at the average annual temperature and increasing temperatures from there, and then getting cold and so on. And then on the over here, we've simply got what I'm calling a frost cracking index, which is simply the amount of time in days that particular depths spend in that frost cracking window. Here I'm defining that frost cracking window as -3 to -9 degrees C. All right, so there's the simple model of diffusion of heat into the ground with varying temperature at the surface, where the temperature is varying sinusoidally on daily and annual periods. You can very clearly see the annual period here. The daily is obscure because it's so small, but here's 15 days. Here's the x-axis zoomed in on 15 days, and the y-axis zoomed in only the top 2 meters. Back to the annual view here. So we've got an average annual temperature of 5 degrees C, and peak-to-peak temperature swings are 30 degrees C, both daily and annually. So that means the coefficient on that sinusoid is 15 degrees C. The temperature fluctuations at depth, you can see, are delayed and attenuated. And actually that attenuation is an exponential decrease with depth in the amplitude. And that the depth scale of that attenuation is we'll call it Z star. And it's the diffusivity times the period divided by pi inside the square root. So again, I'll write that up. Yep, that's the diffusivity. That's the period. So T would either, and this would either be a day or a year. And then just pi. Now, that is the depth at which the surface amplitude will drop to 1 over E, about 1/3 of the surface amplitude. If we want to find, oh, and also, let me just say that I told you what the other things were. The diffusivity here is just 1 millimeter squared per second, like we talked about last time. There were some questions last time about the units on that. Where does that come from? And it comes from simply the fact that in the diffusion equation, or the heat equation, says that the rate of change of temperature is proportional to the second spatial derivative of that temperature. And the units simply work out that that has to be like, that constant of proportionality then has to be length squared per time. You know, we could probably get more profound about it if we wanted, but let's just leave it at that. So again, we've got the annual here, and that smaller graph is just the time spent in the frost cracking window, again, -9 to -3 degrees C. And then here is zoomed in on 15 days and the top 2 meters depth. Now, we can run some rough numbers on this to get a bit of a sense of, before I erase this, sorry, did everybody see my announcement about the quiz? I call it a quiz because the questions should mimic exam questions, but it's really just homework. It's open book, open notes. You can consult with fellow students. I do want you to make sure your answers are your own so that I'm not faced with ethical dilemmas in my grading. Okay, that's already posted on Canvas. It'll go live at noon, and you can do it whenever, and it's due beginning of class on Monday, because the key is already posted and will go live shortly after the beginning of class on Monday. Okay? All right. So, let's run some numbers on these depths. I'm using this depth scale. Now this Z star, let's write it again here, is the depth for 1 over E attenuation. That is, we'll understand what I'm talking about. So if I have a 30-degree swing at the surface, then I'd have roughly a 10-degree swing at this depth, Z star. And if I want to look at what the depth at which I get significant changes in the temperature due to that surface forcing, I essentially just multiply this by 3. And that comes to, I'll just simplify that, so depth for attenuation to 5% of the surface is this delta, and this 1.7 times the square root of kappa times T, again, diffusivity period. In this case, the period's either 24 hours or 365 days. Kappa, again, the diffusivity, 1 millimeter squared per second. Now, when we do these calculations, we've got to make sure we do the various conversions. If I want to know meters, then I need to convert my millimeters squared to meters squared. If I want to know times in, say, days or years, then I need to convert seconds into years or days. So let me, rather than show you a bunch of numbers on the board, let's look at the depth for the daily period. We call that delta sub D for day. And that comes out to be 0.49 meters. And the annual period, let's write yearly period, delta Y is, that depth is 9.5 meters. Okay, so what? Well, let's look here at this cross-cracking index. Again, this is simply the summed up amount of time over the entire year that the various depths in the ground spend within that cross-cracking window. So a decent index of the intensity, or at least the relative intensity of cross-cracking as a function of depth. We see the maximum here occurs at about at about 0.4 meters, and I'll tell you that, to another decimal place, it's 0.37 meters. I just said that where we decline to 0.49, where we decline to 5% of the surface fluctuation for the daily period is half a meter. So we can see the maximum frost cracking occurs near where we've dampened out almost all of the daily fluctuations in temperature. So at that depth where we hit that maximum is where, and literally this precise depth amounts to where we've reached 10% of the surface amplitude. So what that means is that when it's cold, at deep enough, we're no longer swinging above and below the frost cracking index so much, and rather we're spending almost all our time within that window, at least when it's cold like this. What does the other number tell us? That 9.5 meters where the annual fluctuations drop to 5% of the amplitude at the surface. Well, we see here that the frost cracking index drops to 0 at 2 meters depth. 9.5 is quite a bit larger than 2. So what we can, and let's just look back also at the annual. So here's 2 meters up here. What that's telling us is that we still need, because the average temperature is 5 degrees above 0, in order to spend significant time in that frost cracking window, -3 to -9 degrees C, I got to be well above where those annual amplitudes are attenuated to 0. In other words, I need to be in that part of the ground where I'm still getting big annual swings in temperature. And specifically, that 2 meters amounts to where we've dropped the surface amplitude to only 63%. We've only dropped it a bit. We've dropped it to 63% of the surface amplitude. Okay, so that maximum frost cracking occurs. Well, we still get significant frost cracking at the surface because we're swinging in and out of the frost cracking window. But we max it where we get past those surface fluctuations, but we go to 0 well before we reach the damping out point of the annual fluctuation. All right, maybe I shouldn't belabor that anymore. Is that pretty clear?
I don't think so.
No?
I was pretty confused.
Okay. in order to do frost cracking, we need to be in this sort of pale blue to light blue window. Okay, so that's, if we look at here, when we get below about 2 meters, it's never going to be cold enough. Because the average temperature of the year is above freezing. And so if we get deep enough where we attenuate that annual swing to a low enough amplitude, then we're not going to get any frost cracking. We need to be close enough to the surface that we're subjected to cold. But if we're, well, and if we're at the surface, you know, it definitely gets cold enough some of the time. And here again is the 15 days. We can see it definitely gets cold enough some of the time, but it also is too warm and too cold some of the time. So where we really get the kick in major frost cracking is where we've dampened out those daily fluctuations. But we still got to be well within where the annual fluctuations are big. You know, we still, again, we've got to be close enough to the surface to feel that cold from the surface, at least on an annual basis. But ideally, if we're really wanting to break rock, we want to be deep enough to where we're not feeling so much of the daily fluctuation.
I just wanted to know if you ended up looking at the picture of the right side, like the was 0 to 2 meters and 0 to 100 day mark, because that's where the graph is showing. This is,
So this is just a sum of the amount of time in the year that it spends. All right, let me go back to the annual just to make that clear. Okay, so here we see time marching from 0 to 365 days. This is the total amount of time summed over the year spent within the temperature range of -3 to -9.
okay.
Is that?
Yeah.
Yeah, I mean, it's a bit confusing because I'm calling them both time, but yeah. So this is simply the amount of time spent in the frost cracking window, and it's a decent, like I said, a relative index of how strong that process is going to be as a function of depth. And this is just to zoom in on and show you the daily fluctuations. And you can see here, this transition is about, can anybody see that transition from one pale blue to another pale blue? Okay, that's where we go from -3 to -2. Okay, so this is cold enough, this is not cold enough. And we can see that as we get, you know, we're sort of on the warming tail of this cold spell, and the floor of cold enough is coming up and actually going away completely by the time we're out here. You could.
So during the day in the cold months, like you'll have frost wedging deeper down than you would at, like if you can see the difference in the pale blues during the day.
Yeah.
So I guess I'm just kind of thinking out loud. But during the day you'll have like deeper frost wedging or frost cracking, and at night it'll.
Yeah, I mean, it's a bit complicated because you know while at a lot of these depths now I'm not getting frost cracking anymore, but I still will be having some at the surface. It's just that over the course of the day I spend quite a bit of time outside of that window. You know, if we look, I'm really only in that frost cracking window at the surface for a few hours maybe.
Yeah, I was talking about like during the colder months.
Okay, over here.
But I guess it's the same thing. Yeah.
Yeah.
Okay. Thank you.
Sophia?
So I don't know if it matters, but there's the color change on the very left of the graph as well, right there.
Right here?
What is that?
Again, we're just looking at we've zoomed in on this period around here. Okay. And so you see just the annual variation in temperature. So all we're seeing when we zoom in there is that, yeah, over here it's a little bit colder still than it is here. Yeah.
So I'm wondering about this graph, like where exactly does this elevation, does this count So if you're at like sea level and you're 2 meters below, it's not gonna be the same as if you're up in the mountain range.
Well, it just depends. This depth is just relative to the surface, and what we're looking at here is given the temperature fluctuations at the surface. So around here, for example, down in the valley, we're hardly ever going to get cold enough. We'd have to go pretty high up in the mountains to start getting a lot of frost cracking. And in fact, when anybody climbed up Mary's Peak or walked up Mary's Peak, not from the upper parking lot, but say from the lower one, you walk along the slope there and all of a sudden you start seeing those trees with pistil buds. So that's where you start getting frost heat and probably also some frost cracking. That pistil bud tree thing is indicative of heaving at the surface due to frost. And so you don't see it. Of course, maybe you only get the trees that are small enough to show it at the top, but it does seem that you walk up into that band where there's a lot of frost action going on. So again, what this is telling us is simply, okay, given these climate parameters, this is how the temperature propagates, and this is the sort of frost cracking index that I would get. If I change these parameters, I get a different function over there. Okay, so if I go higher, I'm going to get colder overall, and I would have more frost cracking, and it would penetrate deeper. This is not to say that frost cracking only ever goes 2 meters deep. If the average temperature were lower, then it would go deeper. Does that make sense? If the average temperature were higher, it wouldn't go as deep. To the point where if the average temperature is high enough, I would never get frost cracking at all. Yeah?
Like a curve the time frame on the x-axis. If you go back to the last, it looks like 0 starts in the summer instead of
Spring, summer-ish, yeah. I mean, this is fake. Hey, this is fake. I mean, I can show you real data that look similar, but actually correspond to like actual calendar dates. This is just saying, okay, this is, some annual temperature plus sinusoidal fluctuation on a daily scale plus sinusoidal fluctuation on an annual scale, and both are attenuated by an exponential with that z star and blah. So yeah, day 0 is arbitrary. That's kind of why I put down here 1 year starting in spring, maybe ish. Yeah.
Must have missed it, but where did the 1.7 come from for the delta?
That comes from, so that's equal to 3 kappa t over pi.
Okay.
So I just figured I'd make it slightly simpler for you. I mean, if you want to remember this one instead, be my guest. I mean, at least the numbers are fewer digits. So,
Thank you.
yeah. Okay. Well, you'll get more, yeah.
What is the 9.5 meters thing?
So again, what I'm doing here is I'm saying, okay, this is the depth of attenuation to 5% of the surface, given this diffusivity and given the period.
And the diffusivity is the 1
Is
millimeter,
the 1 millimeter squared per second. And so
period
for
would be-
the daily period, for 1 day, t equals 1 day, then delta equals 0.49 meters. For t equals 365 days, delta equals 9.5 meters. And you can, I don't know just how clear it is, but remember I said the average annual temperature is 5 degrees C, so that's right in this sort of yellow here. We can see that as we get down to 10 meters, it's pretty much yellow all the way across, give or take a shade of blue or orange-ish. The colors here are discretized to be about 1 degree per color band. 1 degree C. Cool? All right. I mean, we're cool. Do we understand? All right. So, but now I want to talk about roots. Okay, so that was frost cracking. Frost, sometimes called frost shattering. Same mechanism as frost heave, and we're dealing with heave pressure. But we will talk about frost action again when we get to transport on slopes, because frost heave can push the surface such that we get transport. So just want to be clear, we're, weathering, in terms of weathering, frost cracking, we'll use a different term for transport, although the ice formation mechanism is the same. Okay? Now let's go on to roots, because in a lot of places, the Earth's surface is covered with trees, and those roots penetrate sometimes all the way through the soil into the rock, and get at least wedged in there. And we can see here that, the roots do grow into cracks in the rock. And here's a tree that has fallen over. This is in Maine. And we can see both boulders exposed in the hole made by that tree falling over, and boulders, including this huge one, embedded in the roots themselves. So at least at the point of that tree's uprooting, the roots pull rocks that are broken out of the bedrock. So the question might be, is that the only time that roots break rocks? Do roots break rocks while the tree is still standing? It seems, there are at least cracks for the roots to grow into. There have to be at least cracks for the roots to grow into for this to happen, right? So we need some mechanism for that. Here's just another, big boulder, just showing sometimes these rocks are pretty big. Okay. Oops. This is sort of a common photo on the internet, so I don't know where exactly it comes from, but we see this bicycle embedded in a tree and it's lifted off the ground. Personally, I've always been kind of amazed at how little violence is done to the bicycle by the growing tree. It's deformed a bit, but it's not just twisted ridiculously beyond recognition. It's not terribly deformed. Of course, it didn't have to push against anything. We see here that in an urban setting, the roots are quite vividly mimicking the pattern of the spaces between these bricks. And then the question is, we know that if this, it seems pretty likely if this tree were uprooted that it would take all those bricks with it. But again, do the roots break rock? Let's look at some graphs, some data now. All right. On this top graph, so on all of these graphs, we've got diameter at crest height, dBH in meters, going from 0 to 1.2 meters. So we're not going to the hugest trees, we're only going about this big. And here's the volume of detached bedrock found in uprooted trees here. So we see that the relatively small volume until we hit, say around 0.4, 0.45 meters diameter. We get our biggest values up around 0.7 meters diameter. We might well expect that graph to keep going up if they had measured bigger trees. But the biggest trees were only still smaller than a meter dBH. Here we've got large root biomass, large roots defined as roots with diameters greater than 1 centimeter. And we see how that increases with DBH. And here, a curve of age versus DBH. So we're seeing, okay, where we hit this peak, at least on this graph of volume detached, we're talking trees that are over 100 years old. So the data show that uprooted trees pull up volumes of rock roughly in proportion to the root biomass, which is interesting. Here are some more graphs. We've got on the vertical axis of both of these is soil thickness. So this would be looking at data varying over places where we've got very thin soils to soils up to, say, 1.5 meters thick. So we're looking at a variety of locations in this graph. And on this axis, we've measured soil production rate, or the bedrock soil interface lowering rate, the bedrock lowering rate, as measured from concentrations of cosmogenic nuclides in the rock, actually in the saprolite, if you will. Over here, we have the root soil area ratio. This is given an exposed cross-section. What's the ratio of root area to soil area? And you know, this number is never getting very big. We're maxing out here at 1%, 0.01. And we're showing data for both understory and the large conifers. And again, this is all in the Oregon Coast Range, southern Oregon Coast Range. So here we're seeing that we've got some detailed measurements of soil production rate and detailed measurements of roots. And it appears evident that the depth scales, or the scales at which the production rates and root densities decline with depth, are similar. Not a total smoking gun, but again, consistent with the hypothesis that roots are doing damage. Here we've got some geophysical data. This is the raw ground penetrating radar data. This is the data transformed in order to particularly highlight places where we've got roots that are greater than 2 centimeters in diameter. And on this graph, we're looking at soil depth with distance along the transect. And what we note in particular is that, okay, let's look at right here. We've got a soil depth that is, oh, okay, this is a little bit confusing. But I think this black thing here is supposed to be the soil bedrock interface. And so it's kind of mirrored here, right? Where it's deeper here, it's higher on this graph. But let's look at here for a sec. Our soil depth is, say, around 0.5 meter. So that's just going to be right up here. Again, that black line or so. And we've got lots of places, and we've got lots of big roots below the soil down into the bedrock. Yeah, that's the important point there. All right. So if those are indeed roots, and we're inferring that, from the data, but if those are indeed roots with diameters greater than 2 centimeters, then there must also be cracks at least that size in the bedrock for the roots to be in. And then the question is, how did those cracks form? Did they form from some mechanism other than the roots enlarging those cracks somehow? Now, the question gets to this issue of, okay, do the roots literally physically push the rock apart simply by growing? Or is it something else? These graphs have to do with wind speed and root movement. So we've got a chart recorder on some roots up here, showing root movement in millimeters versus time in days. And down here we've got wind speed. And so we see that when the wind picks up, we get greater root movement. And that movement is going up to around 50 millimeters. So if the root, and this is literally the, I think, up and down motion of the roots. If the roots are moving 50 millimeters, that doesn't necessarily mean that all the rock is moving 50 millimeters with it, but it does indicate that it's, whatever it's anchored in, it's pulling on. Let's look at even some more data. So, yeah. This is seismic intensity in the 3 to 30 hertz band versus time and distance down. Oh, no, wait. No, sorry. This is time, and that's distance east to west. And what we see here is they're sort of highlighting the wind noise from trees. Here's another graph showing the variation in frequency from 0 to 100 hertz in hours, and then this is decibels of seismic noise, and we see this high noise corresponding to, down here we have wind speed, again, versus the same hours. So we see that seismic noise picking up with the wind speed. So we're seeing that whatever energy is being transferred to the ground from the wind through the trees to the ground does actually increase with wind speed, which kind of makes sense. The wind pushing stronger on the trees, it's making more noise in the ground. And note that when I say noise, we're talking way down into subsonic. 3 hertz, that's 3 cycles per second. So, yeah. So it seems that in a forested landscape, we are seeing, if our hypothesis is that roots are breaking up rock, we've got a lot of data that are consistent with that hypothesis. Now, I actually had lunch with a woman yesterday, Jill Marshall, who is trying to get some detailed measurements of this by actually putting little pressure transducers, these little film, like piezoelectric devices that measure force. She's actually putting those in cracks in the rock, putting those between roots and rock. There's some, the technology isn't. She says it's great for showing time signal, but the problem is that for actually showing real amplitude of force, there's a huge amount of drift because, as you squeeze these films, they get damaged and, irreversibly so. So she's working on ways to try to solve that issue. Here, again, we're looking at soil production or bedrock lowering rate versus soil thickness here, just on a 0 to 1 meter scale. And again, looking at this soil thickness, where we're seeing a peak in production rate at around 25 centimeters or 0.25 meters. And the authors that collected this data noted that the rock under less than 15 centimeters soil was less weathered. I want to jump back to these soil columns. It said this soil was about 4 meters thick. This was about 20 centimeters thick. And these two spots correspond to places the thin soil where the lowering rate is apparently very fast, the thick soil where the lowering rate is apparently very low. So it's looking like this soil thickness is about the right thickness for the maximum rate of bedrock lowering. It's interesting to think about, well, why would it actually, if roots are doing it, would we expect this function to max at some finite depth of soil, or would we expect it to max at 0? Well, if we're going to have trees growing, we kind of need a little bit of soil for them to grow in. Not necessarily a whole lot, but some. So again, this is consistent, just simply the fact that we've got this maximum bedrock lowering rate occurring at some finite soil depth that we can imagine roots actually growing in. Again, consistent with maybe roots are doing a lot of the breaking up of the rock. Now, that doesn't necessarily mean that that we can attribute this sort of rinelet formation to roots. Maybe we need the rinelets for the roots to get into and then do the rest of their ripping and tearing and gnashing of teeth and whatnot. All right, so I'm a minute long. I'm going to stop there. Next time we will talk about some salt cracking, some chemistry, try to work our way back to this original question, or consider the different mechanisms that might be responsible. Make sure you download the quiz and get that to me, turn that in beginning of class on Monday. Have a great weekend.